Hello, everyone. Welcome to the Arithmetic Zone. Today, we are continuing our endeavors with the AP Physics C Mechanics 2012 multiple choice set. So, in the last video, we covered the first half of the set, questions 1 to 17. And in this video, we're going to cover questions 18 to 35, finishing off the questions. So, question 18. It states that identical net forces act for the same length of time on two different spherical masses. Which of the following describes the change in linear momentum of the smaller mass compared to that of the larger mass? So when thinking of change in momentum, I think of impulse. These two values are equal to each other, and impulse is equal to F times T. In other words, how long is a certain force applied to the object? So these two objects are of different masses, but we know that there are identical net forces that act for the same length of time on both spherical masses. So if they both experience the same force and it's applied for the same length of time, that means they share the same impulse, meaning that the change in linear momentum also has to be equal for the two masses, meaning that the answer is answer choice C. Number 19, the uniform thin rod shown above has mass m and length L. The moment of inertia of the rod about an axis through its center and perpendicular to the rod is 1/12 ml squared. What is the moment of inertia of the rod about an axis perpendicular to the rod and passing through point P, which is halfway between the center and the end of the rod? So with moment of inertia, it doesn't really mean anything unless we have an axis or a pivot point as a reference. And in this case, our axis is going to be that goes right through point P. And there are actually two ways to solve this question. There's that of the calculus way, which I think is harder, or if you remember the parallel axis theorem, that gives us an easier way to answer the question. And so what the parallel axis theorem is it states that the moment of inertia around any axis, we'll say P in this case, is equal to the moment of inertia of the center of mass of the object plus mr squared, where r is the distance between the pivot or the axis and the center. So in this case, the moment of inertia of P is going to be equal to 1/12 ml squared. It's given to us in the question, but it's also known that any uniform thin rod will have a moment of inertia around the center of mass of 1/12 ml squared. And this is plus m times the distance between the axis and the center, which is given to us as L over 4, that quantity squared. Now simplifying this down a little bit, we get 1/12 ml squared plus 1/16 ml squared. And that fraction reduces to 7/48 ml squared, which is answer choice E. But let's say you don't remember the parallel axis theorem. You can actually go about it using calculus and still get the same answer. So this is actually one of the required integrations of this class. It's I is equal to the integral of r squared dm. And the limits of integration are really important. So when looking at this axis here, you want to think of this as like the axis of an xy plane, with this being our negative and this being our positive. You could also switch it. It's not like in math. You can also make this positive and this negative. It doesn't really matter. And so when looking at it like that, we're integrating from negative 3L over 4 to L over 4. And now you have to account for this dm. This dm is a bit troublesome. So you would use the linear mass density. Lambda is equal to m over L. Rearrange that to get m is equal to lambda L. And then differentiate both sides to get dm is equal to lambda, which is a constant multiple, dl. And for this case, we're going to say that dl is equal to dx. So dm is equal to m over L, that's the value of lambda, dx. And so we're going to get I is equal to the integral from negative 3L over 4 to L over 4 of x squared, or excuse me, I should put the m over L over here since it's a constant, x squared dx. And I replaced the r for x in this case because no matter where alongside the rod you choose to be, it will always be a distance of x units away. It doesn't matter where, it will always be x units away. So instead of r, we can just say that this is x. And then integrating this out, this is equal to m over L times 1/3 x cubed from L over 4 to negative 3L over 4. And simplifying this all out, that's a lot of work, so I won't show it right now. But you do get 7 over 48 ml squared. And that's how you do it the calculus way. It is more work, it is more involved, but it is doable if you can't remember the parallel axis theorem. So now number 20. A certain one-dimensional conservative force is given as a function of x by the expression F is equal to negative kx cubed, where F is in newtons and x is in meters. The possible potential energy function U for this force is, and then they give us the answer choices. So for this question, we need to know the calculus relationship between potential energy and force. That is given by U is equal to the negative integral of force. Now in this case, force is given to us as a function of x. So I'm going to write this in function notation. I'm going to have f of x dx. And then I'm just going to sub in the force function right inside the integral. So because we are integrating with respect to the variable x, this k is going to be treated as a constant. And so this negative k is going to be pulled outside the integral. A negative times a negative is a positive. So that just goes away. So we get k times the integral of x cubed dx. And then using the power rule, we get that u is equal to 1/4 kx to the 4th plus c. There is actually a plus c because we didn't use any bounds for our limits of integration, so it's an indefinite integral. But we're asked for a possible potential energy function, and none of these answer choices have any constant attached to the kx term. So we can actually just say that c is equal to 0 for this case, and u be equal to 1/4 kx to the 4th. And this is a possible potential energy function, and this aligns with answer choice D. Now 21. Which of the following is a differential equation that correctly describes Newton's second law for a simple harmonic oscillator of mass m and restoring force constant k? I want to focus on the Newton's second law part first. You know that F net is equal to ma, that's Newton's second law. And when dealing with simple harmonic motion, we're really dealing with springs. And we know that the spring force is equal to negative kx for an ideal spring. And because we're asked to relate the two, we can say that this force, the spring force, is equal to the net force. So we can equate the two values. Negative kx is equal to ma, but the question asks for a differential. So you can see that in the answer choices, there is no a. So we're going to have to change this value of a into a different form. So when changing acceleration into a differential, my mind first goes to m dv dt. So let's look at the answer choices for dv dt. C looks promising because its right-hand side is good, but it has negative kv, whereas we have negative kx here. That v kind of came out of nowhere, so we're just going to x that out. And same thing with e, we have the negative kv, but we also have an mg, so that's nowhere in our equation, so we can also get rid of that. So instead of dv dt, we can express this a as the second derivative of x, second derivative of position, if you will. That's another way of expressing a as a differential. And with this new definition, we can see that the answer choice aligns with B. Now, the next three questions come as a set that relate to this diagram. So the question states, an elliptical orbit of a comet is shown above. Positions 1 and 2 are, respectively, the farthest and nearest positions to the sun. And at position 1, the distance from the comet to the sun is 10 times that at position 2. So I just want to label the diagram really quickly just to see what's happening here. So from this distance right here, it's going to be R2. And this distance is going to be R1. It's the distance from the sun from position 2, R2, and the distance from the sun from position 1, R1. And it is stated that at position 1, the distance from the comet to the sun is 10 times that at position 2. So we can also write that as 10r2. That might come in handy later. This is just annotating what I see. So at position 2, the comet's kinetic energy is. So before we look at kinetic energy, I actually just want to focus on gravitational potential energy right now. And that's given by G m1 m2 over r squared. So we can assume that gravitational potential energy is the only force that's present. So we can say that Fg is equal to F net. And in this diagram, the greatest gravitational potential energy is actually going to occur at position 2. It's going to have the greatest Fg. And this is because the distance from position 2 to the sun is the nearest. This is the smallest distance from the sun that is possible in this elliptical orbit as shown by the question. And Fg is governed by this formula where a smaller radius will equate to a larger Fg. So because this is the smallest distance, it will have the greatest Fg. And now since we've established that Fg is equal to F net, we can say that Fg is equal to ma. And I actually want to represent A as a differential. So we're going to say that Fg is equal to m dv dt. And I represent it as dv dt because this stands for instantaneous velocity. So the instant when the comet reaches point or position 2, it is going to have the greatest velocity or speed, I should say, compared to anywhere else in this orbit. Because Fg, the value of Fg is changing with position. The mass isn't changing, so the speed also must be changing in order for this equation to be true. So if it has the greatest speed at position 2, let's write out the equation for kinetic energy. It's equal to 1/2 mv squared, where it is governed by speed. The greater the speed, the greater the kinetic energy. If it has the greatest instantaneous speed at position 2, it will also possess the greatest kinetic energy, which aligns with answer choice C. 23. This also relates back to the diagram, by the way, these two questions. What is the ratio v1 over v2 of the speed of the comet at position 1 to the speed at position 2? Now, this is an elliptical orbit. You can say that the comet is rotating around the sun, so our rules of angular momentum apply. So we can say that the angular momentum at position 1 is going to be equal to the angular momentum at position 2. And just writing out the definition of angular momentum, we're going to have m b1 r1 is equal to m b2 r2. I'm actually going to rewrite r1 as 10 r2 as established in the diagram. We're going to have m b1 10 r2 is equal to m b2 r2. So the m's are going to cancel out, not the b, and the r2s are going to cancel out. So we're going to have 10 b1 is equal to b2, and we want b1 over b2. So we're going to divide by b2 on both sides. So we're going to have 10 with v1 over v2 is equal to 1, but we don't want that 10 included, so we're going to divide by 10 on both sides. And so v1 over v2 is going to be equal to 1 over 10, and that is choice B. Now for question 24, what is the ratio F1 over F2 of the force of the comet at position 1 to the force on the comet at position 2? Now this is going to be governed by our Fg, it's equal to G m1 m2 over r squared. Now, before even going in with the calculations, the only thing that's going to make a difference in this Fg is going to be the position. G is a constant, m1 is the mass of the comet, m2 is the mass of the sun. This numerator doesn't change no matter where the position is, but r2, or rather r squared, does, and that'll influence the value of Fg. So at position 1, we're going to say that r1 is equal to 10 r2. So Fg is equal to G m1 m2 over 10 r2 squared, which is just G m1 m2 over 100 r2 squared. Now for number 2, rather at position 2, It's going to be G M1 M2 over R2 squared. And that's really it. We can't really simplify that any further. So now we need to get F1 over F2. So we're going to just write out what we got. GM1 M2 over 100 R2 squared all over GM1 M2 over R2 squared. And this whole thing simplifies to 1 over 100, which is answer choice A. 25. A block of mass M is pulled across a rough surface as shown above. The coefficient of friction between the block and the surface is mu kinetic friction. So that tells us that the block is moving. The force F that pulls the block is exerted at the angle phi shown, Which of the following is an expression for the magnitude of the frictional force on the block if it is moving at a constant speed? Now, this is important, this last part, constant speed. This means that acceleration is 0, which means that F net is also equal to 0. All of the forces have to cancel out. So it's with these types of questions where drawing a free body diagram is really useful. So we have a friction force directed opposite the motion. This is going to be our friction. We have a gravitational force, Fg. We have a normal force, Fn. And we're going to split this F into components, where this is F sine theta, and this is F cosine theta, or rather phi. I should be using phi instead of theta. So we know that friction is going to be equal to mu k Fn. Well, in order to find Fn, we need to find F net in the y, which is going to be equal to 0. And it is the sum of all of the forces in the y, in the vertical direction, I should say. So 0 is going to be equal to Fn plus F sine phi minus Fg. Now, Fg can be rewritten as mg, and that I'm going to bring that to the other side, with mg is equal to Fn plus F sine of phi. And so Fn is going to be equal to mg minus F sine of phi. And then substituting that right back into our equation, we get that F is equal to mu kinetic times mg minus F sine phi, which is answer choice E. Number 26. Two 4-kilogram blocks hang from a rope and passes over 2 frictionless pulleys, as shown in the figure above. What is the tension in the horizontal portion of the rope? This right here. If the 2 blocks are not moving and the rope and the 2 pulleys have negligible mass. So since the pulleys have negligible mass, the tension across the rope will be the same. And it is said that these 2 blocks are hanging, which means they're at rest, meaning that acceleration is 0. Thus, F net is also 0. There is no F net in the x direction. That's 0. There's no horizontal forces. It's all vertical on the blocks. So F net y is also going to be equal to 0. And it's going to be the sum of all the forces in the y direction, which is our Fg and our tension. So 0 is going to be equal to our tension force minus Fg. You can rewrite that as mg, and 0 is going to be equal to t minus, it's going to be 4 kilograms times 10. So 0 is equal to t minus 40 newtons, which means t is equal to 40 newtons, which is answer choice D. Great. 27. A person throws a ball of mass 0.2 kilograms. The ball starts from rest, accelerates horizontally and uniformly through a distance of 0.9 meters and leaves the person's hands at 30 meters per second. The average horizontal force applied to the ball by the person's hand is. So we're given mass and we want to find the net horizontal force. So we need the acceleration. And we can actually find that through our kinematic equation. So we want to use the kinematic equation that doesn't require time since we're not given that in this question. And that is our Vx squared is equal to Vx naught plus 2a delta x. I'm using x because we're talking about the horizontal direction, and we're given that it starts at rest. So this is going to be equal to 0. We have bx squared is just equal to 2a delta x. And we're given that it leaves the person's hand at 30 meters per second. So we're going to put 30 here. 30 squared is equal to 2a, and the delta x is 0.9. And we get that a is equal to 500. And now we can use the F equals ma property, Newton's second law. So F is going to be equal to 0.2, that's the mass, times the acceleration, 500, and that is equal to 100, which is D. 28. A railroad car of mass 1,500 kilograms rolls to the right at 4 meters per second and collides with another railroad car of mass 3,000 kilograms that is rolling to the left at 3 meters per second. The cars stick together. It's going to be an inelastic collision. Their speed immediately after the collision is. I'm going to draw this out just to emphasize the importance of direction. So this is going to be before the collision. We're going to have our 1,500 guy there, and this is going to be our 3,000 guy. And this is rolling to the right at 4 meters per second, and this is moving to the left at 3 meters per second. So these are velocity vectors, so the direction matters. So we need to establish which direction is positive and which is negative. I like to say that the left is negative and the right is positive. Now we can go on with our conservation of momentum formula. We need to sum the individual momenta of the system. So M1, this will be M1, this will be M2, B1, B2. So M1, B1 plus M2, B2 is going to be equal to the conjoined masses because they stick times the new velocity of the conjoined system. So we're just going to plug in these values. And now here we need to be careful. We have our 3,000, and it's going to be -3. And we're going to add the masses times B prime, and B prime is going to be equal to 2/3. If you get that as a negative number, it's fine because it's talking about speed, the absolute value. So it's going to be A regardless. 29. A meter stick of negligible mass is placed on a fulcrum at the 0.4 mark with a 1 kilogram mass hung at the 0 mark and a 0.5 kilogram mass hung at the 1.0 meter mark. I just want to draw this out really quickly. This is going to be our meter stick. I will say that this right here is our 0.4 mass. That's where our fulcrum is going to be. So this is going to be 0.4 meters. And then the rest is going to be 0.6. Since it adds up to 1 meter. And we're going to have a 1 kilogram mass hung here, 1, and a 0.5 hung here. So 1 kilogram mass is hung at the 0 mark and the 0.5 at the 1 meter mark. Immediately after release, the magnitude of the net torque on the meter stick about the fulcrum is most nearly. So our torque is going to be equal to the cross product of force and position, its distance from the fulcrum. But because the two vectors are going to be perpendicular to each other, the force is going to be acting downwards, and the position vectors are going to be directed towards the fulcrum. It doesn't matter. It's just going to be torque is going to be equal to F times R without the sign. So T1 is going to be equal to 10 newtons. That's the weight, because down here, this is Fg. So the weight is 10 newtons, the mass times G, times its distance from the fulcrum, which is 0.4. This is going to be equal to 4. And T2 is going to be equal to 5. That's its weight, again, 0.5 times 10, times its distance from the fulcrum, which is 0.6, which then is 3. But because these vectors are in opposite directions, one of them has to be negative. I'll just make the smaller one negative. So 4 minus 3, so it'd be T1 minus torque 2, torque 1 minus torque 2, I should say. 4 minus 3 is equal to 1, and that is going to be our net torque. Question 30. An object undergoes simple harmonic motion along the x-axis shown above, where x is 0, where x equals 0 is the object's equilibrium position. Which of the following graphs best shows the relationship between the object's acceleration a and its displacement x from equilibrium? And we're going to assume that positive a to be acceleration directed to the right. So again, with simple harmonic motion, we're thinking of springs. And so I'm just going to write out the force for an ideal spring, negative kx. And again, we're going to assume that this is the only net force available. Not available, but present. So we're going to say that MA is equal to negative kx. And because we're finding the graph of A compared to x, we're going to isolate A. And we get that A is equal to negative k over mx times x. And this is actually in the form of y equals mx plus b. It's going to be a straight line. It's a linear graph. So we can immediately eliminate c, d, and e. C is an absolute value function, and both d and e are parabolas. And I want to look at the slope. The slope of the acceleration function is negative k over m. So k is a positive constant, and mass is always positive. So the slope is negative. It's going to have a negative slope the whole way down, and that aligns with graph A. 31. Ball 1 is dropped from rest at time t equals 0 from a tower of height h as shown above. At the same instant, ball 2 is launched upward from the ground with initial speed v naught. If air resistance is negligible, at what time t will the two balls pass each other? This is a really interesting spin on the kinematics unit. So the one equation that's going to govern the motion of both of these balls is going to be y is equal to y naught plus v y naught t plus 1/2 and the y t squared. So let's focus on ball 1. We know that it's dropped from rest, so the v y naught t, that's just going to go to 0. So it's just going to be y is equal to y naught plus 1/2 in the yt squared. And y naught happens to be h, that's the height that is at. So it's h plus 1/2 in the yt squared. Now for ball 2. Its initial height is 0. So that isn't going to play a factor into it. So the equation that governs this one is actually just going to be v y naught t plus 1/2 and the yt squared. And we can't really do much with that. And we want to know at what time t will the two balls pass each other, meaning that the value of y for both of them, they're actually going to be the same. So we can set the two equations equal to each other. So we have h plus 1/2 in the yt squared is equal to v y naught t. I'm going to move this over a little bit. V y naught t plus 1/2 and the yt squared. And they both share this 1/2 and the yt squared, so we can just eliminate them both. And so we have h is equal to v y naught t, and solving for t, we get that t is equal to h over v y naught. And you may notice in the answer choices, they don't specify whether it's in the x or in the y direction. They probably should, but they don't. And so the answer choice that aligns with this one is C. 32. Suppose that the potential energy of a particle constrained to move along the x-axis can be described by the function u of x, I should say, is equal to 1/2 kx squared minus alpha x, where both k and alpha are positive constants. Stable equilibrium points about which the particle oscillates are located at, and then they give us x values. So this is admittedly a really hard question. So you have to recognize that this is a parabola and that the stable equilibrium points are going to be located at the axis of symmetry. And that's given by the formula negative b over 2a for a quadratic. And this is going to be ax squared minus bx. That's the form it takes. So B is equal to alpha, negative alpha, I should say. So we have negative alpha over 2 times A is going to be 1/2 K. This is going to be alpha over K. And this parabola is going to be a parabola that faces upwards. It has the U shape because A is a positive number. So it's going to look something like this. I don't know its exact placement along the graph. And this axis of symmetry is going to fall alongside where X is equal to alpha over K. And this is going to be where the potential energy is at its minimum. And that's what is encompassed by stable equilibrium points where the particle oscillates. And so our answer choice is going to be B, alpha over K only. This was a really weird question, honestly. It required you to go back to some algebraic concepts that may have been a little fuzzy. This might be a question that you skip if you see it, which no shame in doing so. Number 33, a ball of mass m pulls vertically hits the floor with a speed vi and rebounds with a speed vf. What is the magnitude of the impulse exerted on the ball by the floor? So as we stated before, impulse is equal to the change in linear momentum. So that's what we're going to be focusing on right now. I'm going to draw out this diagram. This is going to be our ball. Its initial speed is vi, and then it rebounds with speed vf. So delta p is equal to m times this velocity vector, the final velocity vector, minus the initial velocity vector. So this seems like it aligns with answer choice B, but we need to look a bit deeper into the direction of the vectors. We need to assign which direction is positive and which is negative. I'll say that up is positive and that down is negative. So now with this information, we can say that delta P is equal to m times Vf minus negative Vi, because that vector is pointing downwards, which we've established to be negative. And now the question turns into, or the answer turns into Vf plus Vi. So it's actually answer choice C, not B. Now we have the last two questions of the test. A particle moves in a circle in such a way that the x and y coordinates of its motion, given in meters as functions of time t and seconds r. X is equal to 5 cosine of 3t, and y is equal to 5 sine of 3t. So these are parametric equations, which are a tough bunch. They're not really that common in physics, but they can appear. And so I'm just going to draw the circle in which the particle moves in. We want to know the radius of the circle. So because this is given in x and y, I'm going to plot this on the x and y plane. And a property of sine and cosine is that their max is 1 and their min is -1. So the max x value that this can attain is going to be 5, and the min x value is -5. And the same applies for the y. So graphing this is going to be the max value that the particle can move in the x direction, and this is going to be the minimum x value that the particle can move in the x direction. And similarly, this is the minimum y value that the particle can attain in the y, and the maximum that it can attain in the y, with a diameter of 10, meaning that the radius is 5. For that one, you had to know the properties of your trigonometric functions in order to establish that, but the radius is going to be 5. Now 35. Which of the following is true of the speed of the particle? Now, if you're taking AP Calculus AB, you might approach this differently than those who are not taking the course, because it is known that the speed of a particle is given by the square root of the derivative of the x squared plus the derivative of the y squared. And I just want to address that the speed of the particle will be a single number. It won't have a range. So C, D, and E are out. This is because this particle is in circular motion. I'm going to redraw that circle. This particle is in circular motion, meaning that its tangential speed, so it's going to face perpendicular to the centripetal acceleration no matter where it's at. But the speed at which it travels is going to remain constant because there is no tangential acceleration. So the speed will remain the same, but the velocity will differ. It's going to rotate around the circle at the same speed no matter what. So going back to this Calc BC method, where we know that the speed of the particle is given by this differential equation, we can say that dx dt is equal to -5, or -15, excuse me, sine of 3t. And dy dt is equal to 15 cosine of 3t. So we can actually let t equal anything because we know that no matter what the t value is, the speed will always be the same. So let's let t equal to pi. So now we have b of pi equal to, and I'm just going to plug this in, -15 sine of 3 pi squared plus 15 cosine of 3 pi squared, the whole thing squared. And this is going to give us an answer of 15, which is B. I'm sure there are other ways to approach this without having to use AP Calculus BC knowledge, since the AP Physics C course is available to any student who has taken calculus, even Calc AB. So if there are other ways, let me know. But this is, for me at least, the most efficient manner of tackling this specific question. So there we go. This was the whole multiple choice set. Obviously, we took a bit longer than how it should normally take. So some test taking tips that I would advise you to do is whenever you see a question that's hard or that you know will take a lot of work, you should just skip it. You should only be tackling questions on the test that you know you can get and that are free points. You want to maximize the amount of points that you can get. So don't feel discouraged if some of these questions threw you off. They definitely threw me off the first time I did some of them. And you got this. Good luck on your AP exams.